Okay, this is Dr. Kraus, and this is basically me continuing to lecture after class has ended, which you might argue is completely unfair, but I didn't give you any homework today, so I think watching this is okay. And it's not entirely required. Some of it's really good. You guys are pretty sharp, and so most of you already have a form for the data that you need to fit um, for the answers to the lab questions on this Friday for Lab 2, the comprehension questions. Um, sorry, let me turn that exposure lock on. But in case you don't, I guess I'm just standing in front of the light creating weird shadows. Sorry about that. In case you don't, I want to help you know how to do kind of my version of Laplace for underdamped second-order systems. I think there's a right way to do the mechanical or the mathematical form of that and a wrong way. And my way is to basically use my abbreviated Laplace table, which not everyone is on board with. So let's just talk about that. So if I had this system, it's a mass spring damper system, underdamped second-order system, and I wanted to find its transfer function, I would draw a free body diagram of this. And so I'll have kx and bx dot going like that. And so if I sum forces, I will get that f minus kx minus bx dot is equal to mx double dot. So if I take and add those two across, I get that mx double dot plus bx dot plus c plus kx is equal to f. And then if I Laplace transform that, I get ms squared plus bs plus k times x is equal to f. And so my transfer function, my g of s, we're talking about x of s divided by f of s. So I'm dividing this stuff across. I get 1 over ms squared plus bs plus k. But if I multiply through top and bottom by 1 over m, it turns out that I can get my transfer function into a form that I prefer. So I'll have 1 over m in the numerator, and I'll have s squared plus 2 zeta omega n s plus omega n squared in my denominator. And I prefer that form because I know how to estimate things like the natural frequency and the damping ratio from looking at the data. And it's not always obvious how to estimate B and K per se. So if I have this as my transfer function, then my step response, basically I'm saying that my input is just 1 over S, so then my output would be 1 over S times G of S, which is 1 over m s times s squared plus 2 zeta omega n s plus omega n squared. And if you're looking at the abbreviated Laplace transform table that I have provided for you, you'll notice that that is simply not in there. And I must be really, really mean, and I'm okay with that. Because I want you to learn how to use the Laplace transform in a way that you'll remember for the rest of your careers. And so rather than give you a gigantically long table where you're always trying to find the magic stuff, I want you to remember maybe half a dozen Laplace transforms and then a couple of different properties. And so one key property that we need has to do with exponential decay of sine waves. With these kind of mechanical systems, we often end up with step responses that look something like that. And so it has some kind of an element that looks like e to the negative something times a sine or cosine of something. And so there's a property in the Laplace transform table that I have provided for you that does tell me that I have e to the negative at times some f of t when I Laplace transform that. I simply take f of s plus a. So what that means is, if I know, for example, that the Laplace transform of sine of omega t is, I want to embarrass myself here, but I want to say that's omega over s squared plus omega. I should double check that really fast, but that is definitely one that I should remember. And I did not embarrass myself, so that is true. Then what we're saying is that if I want to know the Laplace transform of this, then wherever I have s, I'm simply going to plug in s plus a. And so this should produce omega over s plus a squared plus omega squared. Like I said, I don't expect you to memorize this form. I expect you to memorize this principle. And so similarly, the cosine of omega t has a Laplace transform of s over s squared plus omega squared. And that's one of the ones that I would expect you to remember off the top of your head. A step, an impulse, maybe a ramp, sine and cosine. And I think you can get pretty far with just knowing those things. Then the integration and differentiation and these kind of time delays, those kind of principles. But you only have to know just a few of these and then the principles to get the rest. So in this case, there are two places where I have to plug in s plus a. And so the Laplace transform of the cosine times e to the negative t is s plus a over s plus a squared plus omega squared. So if I have a step response times a decaying sine or cosine, and it might include both sine and cosine, then I need to have a term that looks like, a term that looks like this and a term that looks like this. Pay no attention to this other thing that I started to circle. So if I know that the x of s for this thing that I'm trying to inverse Laplace is 1 over s times something over s squared plus 2 zeta omega n s plus omega n squared, I'm saying there's probably a decaying sine and cosine here, and then the step response. And so I think we want to look for a over s plus b times omega plus c times s plus a divided by s plus a squared plus omega squared. So this part is the sine term, this part is the cosine term, and we're adding those two together to get to this form. I guess I sort of skipped a step there if I'm trying to be absolutely clear. Let me write that out for just a second. So what I'm saying is that a over s plus b omega over s plus a squared plus omega squared plus c times s plus a over s plus a squared plus omega squared is the form that we're trying to use. And so we're combining those two together because they have a common denominator. And again, is this shorter than using a Laplace transform table that has more stuff and therefore provides you with magical answers? No, it's obviously longer, but I think it's something that you'll understand more, learn more from, and remember longer. And so the question is, how do I take this form and set it equal to 1 over s times 1 over m divided by s squared plus 2 zeta omega n s plus omega n squared? So you might argue that I've made this problem worse instead of better. I now have to find a, b, c, omega, and a. That seems complicated. But the first step is that in order for all of this to work, this denominator must be the same as this denominator. So I'm going to use that to find a and omega, and then I'll do regular partial fraction expansion stuff to find a, b, and c. So if s plus a squared plus omega squared has to be equal to s squared plus 2 zeta omega n s plus omega n squared, I'm going to multiply this term out over here. And so I'll get s squared plus 2as plus a squared plus omega squared is equal to s squared plus 2 zeta omega n s plus omega n squared. And if this is going to be valid, it has to be valid for every power of s. So I've got some s squared terms, but they just tell me that s squared is equal to s squared. So that's true but not helpful. Then I've got s to the first, and then I've got s to the 0. Let's start with s to the first. That looks like the most helpful. And so what we're saying is that 2a is equal to 2 zeta omega n. So I'm grabbing this term over here on the right and this term over here on the left, and I divide by 2, and I plug that into my TI-89 calculator, and I determine that a is equal to zeta omega n. Okay. Then I can take that information. My s to the 0 equation tells me that a squared plus omega squared is equal to omega n squared. And so if I take this result and plug it in here, we're saying that zeta squared omega n squared plus omega squared is equal to omega n squared. So I'm going to subtract that across. Omega squared is equal to omega n squared minus zeta squared omega n squared. Pull out an omega n, take the square root, and omega is omega n times the square root of 1 minus zeta squared. And it turns out that is what vibrations people would call omega d for the damped natural frequency. Okay, so I know in summary so far that a is equal to zeta omega n, and my omega is really equal to omega d. So that can tell me that once I find a, b, and c, I know the form of what my final inverse Laplace will look like because I know a and omega n. Sorry, little a and omega n. Sorry for the confusion there. So I'm going to have my x of t is going to have some a times 1 of t, that'll be a step response, plus b times e to the negative zeta omega nt sine omega dt, plus c e to the negative zeta omega nt cosine omega dt. Because this is the a that we found, and this is the omega that we found. So I'm heading towards that form, and the question is, a is equal to what, b is equal to what, and c is equal to what? And if we go back to this equation, if this denominator is now the same, I can multiply through on the left and the right by either form of that, and they're the same, so they would cancel. So I'm going to take this whole equation, I'm going to multiply it through by s squared plus 2 zeta omega ns plus omega n squared. So everything over here on the right is going to cancel in the denominator. And then on this term, this s will cancel that s. And in this term, this will cancel that. Even though they don't look the same, we've already done the math and chosen a and omega n to make sure that they are the same. So what we end up with is that a times s squared plus 2 zeta omega ns plus omega n squared plus s times b omega d plus c times s plus zeta omega n is equal to 1 over m. So again, I'm saying that this s cancels that s to produce this term, and I'm saying that this denominator cancels that term to produce this term. Okay, and so if I multiply some of this stuff out, I'm saying that as squared plus a times 2 zeta omega n s plus a times omega n squared plus bs omega d plus c s squared plus cs zeta omega n is equal to 1 over m. And again, I've got s squared terms, I've got s to the first terms, and I've got s to the 0 terms. And so my s to the 0 tells me that a omega n squared is equal to 1 over m, which does help me find a. That might not be super obviously clear why that's true, but we know, or we should know, hopefully, that omega n is a square root of k over m. We kind of skipped that step or whatever. So if I plug that back in, we're saying that a times k over m is equal to 1 over m, which implies that a is equal to 1 over k. All that's telling me is that my steady state response is going to be, my displacement will be f divided by k, which is just a restating of the spring constant. So that makes intuitive sense. So I know a. Considering a to be known, I can now come into here, and I can say that s squared tells me that a plus c is equal to 0, which implies that c is equal to negative a. And then if I take that information to my s to the first equation, I get that a times 2 zeta omega n plus b times omega d plus c times zeta omega n is equal to 0. Well, if this is just negative a, then this one cancels one of these. And so we're saying that a times zeta omega n plus b times omega d is equal to 0. And we said previously that omega d is equal to omega n 1 minus zeta squared square root. And so if I plug that in, I get that a zeta omega n plus b omega n 1 minus zeta squared square root is equal to 0. I can divide omega n out of both of those. I'm going to subtract this term across, divide that across, and I'm saying that b is equal to a negative a zeta over square root of 1 minus zeta squared. So the final step in this then, plug all of that back in, pull out an a, and I think that what we're saying is that x of t, sorry, my pencil lead is running out. So I've got an a times 1 of t, and then that'll be a minus zeta 1 minus zeta squared square root times e to the negative zeta omega nt times the sine of omega dt minus e to the negative zeta omega nt cosine omega dt. So that's just to say that b is equal to negative a zeta over 1 minus zeta squared, and c is just equal to negative a. So I wanted to clean that up just a little bit more. I could substitute in my 1 over k for a if I wanted to. I can pull out my negative e to the minus zeta omega nt, and then I'll write that as cosine omega dt plus zeta over 1 minus zeta squared square root sine of omega dt. And so that is the final form of how I would do inverse Laplace and I would use this for the step response data fitting for lab 2. The one trick being we did not consider the possibility that what if the gain, I guess you could just kind of consider this your gain as whatever's in your numerator and just call this, something like your C of 0. And then you could set up like an omega n is equal to C of 1, and your zeta is equal to C of 2, and then define omega d is equal to omega n times the square root of 1 minus zeta, and obviously you can't really use the Greek zeta, so I'll use that as a z, but I'm kind of mixing Python code and just symbolic math here. But yeah, I think those, so there's a gain there on the outside. Omega n and zeta are your unknowns in this curve fitting, and so those would be the 3 things that your myModel function would take as inputs, or your myCost would try to determine for you using optimize.fmin. I think you should be all set. Let me know if you have any questions.